Hello everybody, we are going to be talking about rank today, and this is yet another instance in linear algebra of something that we've been talking about, and we know what it is already, but we're just giving it a specific name. All right, and rank here, there's a couple of different ways to define it equivalently, but one way is that rank is the dimension of the column space. And let's remember, right, dimension is the size of a basis, okay? And how did we find a basis for the column space? Well, we figured out where the pivots were, and each pivot column gave us a vector in that basis. So another way to define this is the number of pivots in A, or the number of pivot positions in A. All right, now let's talk about the rank theorem. Okay, and this is sort of just restating something that's important, but that we've already talked about a little bit in previous videos. Okay, so first part of this theorem is that the dimension of the column space of A is equal to the dimension of the row space of A. And row space is going to be similarly defined as column space, right? Linear combinations of the rows, and we'll talk about that in just a second. But the main thing here in this theorem is this following the rank equation, okay, which is that the rank of A plus the dimension of the null space of A is equal to n. All right, and let's break this down. So n here is the number of columns. Dimension of null space, we got that by finding the number of non-pivot columns. And rank is the dimension of the column space, which is the number of pivots. So we sort of get this equation just based on definitions of things and how we find bases for things. So the number of pivot columns, the number of non-pivot columns, well, that's just the total number of columns. Pivots tell you the rank or dimension of the column space. There we go. And non-pivot columns tell you dimension of the null space. Okay, so let's take a little detour and talk about row space. All right, row space of A. So let's have A is an m by n matrix. All right, and row space is a subspace of R. So A here, there's m going this way, and there's n going this way. So we're looking at each row has n entries. So this is a subspace Rn, and it is the span of the rows of A. Okay, and oftentimes here we'll go ahead and write, since we're viewing them as rows, we'll write the rows as R1 is, something and then something else. We'll write them as row vectors just because it's easier to visualize that way, right? Reconcile it with this is a vector that's a row of our matrix. All right, finding a basis for the row space. It's going to be kind of similar to finding a basis of the column space. Okay, so you need to row reduce to find where the pivots are in A. And then we're going to use a theorem here. This is theorem 4.6.13 that says, among other things, if A and B are row equivalent, then the row space of A is equal to the row space of B. So what we're saying is row operations don't change row space. Okay, so what that means is you need to find out where the pivots are in A, but then once you know where the pivots are, basis for row A is those pivot rows. Okay, and with column space, you had to go back to the original matrix to get the basis. With row space, it doesn't matter, okay? So you can do the original rows or the rows in the row reduced matrix. Both form a basis because both are linearly independent sets that generate the row space, and the row space of the original version is the same as the row space of the row reduced version. Wonderful. All right. So let's go ahead and look at an example. Okay. All right. So A is the following matrix: 1, -1, 5, -4, 2, -6, -1, 5, 0. That is row equivalent to B, which is here 1, 0, 0, 0, -2, 0, -1, 5, 0. Okay. So first, A is row equivalent to B, and that tells us where the pivots are. So here's a pivot, here's a pivot. Great. And let's see what we want to do first. List the rank of A. Okay. So rank of A is the number of pivots, which is 2. Okay. And then we want to list dimension of the null space. Okay, that's the number of non-pivot columns, or another way to think about it is the number of free variables, which is 1. And then we want to find bases for various other things. So a basis for the column space. Let's do that first. Basis for the column space. You look at the pivot columns and then you go back to the original matrix. So first column, but in the original matrix, 1, -1, 5. And second column is also pivot. Go back to the second column in the original matrix. Okay, there's our basis for column space. Basis for, let's go ahead and do null space. Actually, let's not do null space next. Let's do row space. Okay, basis for row space. So now we want to figure out where the pivots are, but we want the pivot rows. And you can go back to original rows, or we can just use the row reduced rows, which is what I am going to do. And I am going to write them as row vectors just because that meshes a little better with how we write this matrix. Okay, there's a basis for row space. And now to get a basis for null space, remember we need solutions to AX equals 0 in parametric vector form. All right, the tempting thing is just, oh, here's my non-pivot column, that's my basis, but that's not how it works. So let's remember how it works. Okay, so X is equal to, I have 3 variables, X1, X2, X3. And X1 is going to be positive x3, right? There's negative 1 x3, move it over. Let's see. Ooh, this is not row reduced all the way. So let's divide this by -2, divide this by -2. So that new row is 0, 1, -5/2. So x2 is going to be 5/2 x3, and then x3 is free. Okay, and when we write that in parametric vector form, you're taking out that free variable. That leaves there's 1 here, 5/2 here, and 1 here, and this vector is the basis that we want. So basis for the null space of A is this vector 1, 5/2, 1. And there we have it. Okay, that's all.